Lab 2, Two-Dimensional Motion by Shervin Praveen. Introduction. The purpose of this lab is to measure an object's motion in 2D and compare it to our models. We want to measure how impactful air resistance is, and we want to find the coefficient of drag on our paper ball. The preview. We learned air resistance plays a big role on our projectile, and we will also see why the graphs differ so much. The main ideas and principles. F equals ma. We use this formula to calculate force from gravity. The second equation, we use this formula to calculate what the constant of drag is, and we use the velocity update to calculate the velocity throughout the trajectory. These are the main physics ideas and principles. Reason for each model. F equals ma. To show gravity gives us constant deceleration. The drag force formula to calculate resistance against velocity's direction. The velocity update to show how the velocity is constantly changing. And we use tracker for actual position and glow script for expected and real predictions. The initial conditions. The paper ball starts at the origin. The ball has constant deceleration throughout the entire motion from gravity and drag. The velocity initial is measured, and the position is 0. The system is the paper ball, and the surroundings are the earth, the air, and everything else. The details. We started with tracker. We set the starting point as the origin, and we set the scale using a meter stick, and we plotted the points during the 0.7 seconds. We then modeled the findings through glow script. We set net force equal to the force of gravity plus the force of drag. We then plugged this into the velocity update formula and compared the three graphs, the actual, the modeled, and the no drag prediction. These are the coding details. You can see it on the left. We created a formula for drag. We inputted the velocity magnitude and velocity top hat into the force formula for drag, and then we set the net force to be force of gravity plus the force of drag. As you can see on the left, we found the constant is 0.001749. The similarities and differences. The similarities we found. Our models we created off tracker was very accurate. We see little to no mistakes because we are taking into account most of the forces acting on our object. The differences. It's not exactly perfect, but the drag changes with the shape of the paper ball. As you can see on the graph, the blue and red graphs, the lines are pretty similar. The sources of this error. It's almost impossible for a model to be perfect. We need to take into account of how the paper ball isn't shaped perfectly. The two research questions. The first one asks, do our models predict terminal velocity, and if not, how can we? Our models don't exactly predict terminal velocity because terminal velocity comes within some time and a lot of acceleration. And if not, how can we? As you can see, our graphs, they approach terminal velocity, and you can see they are approaching a constant velocity. But if we want to model it, we would have to give it some time until it leveled off to one constant velocity. Next question asks, if the ball was thrown straight up into the air instead of as a projectile, would it take longer to hit the ground? It would not take longer to hit the ground since the x component does not affect the y component. We can see this on the equation of the kinematics for position. If we use just the y position in our kinematics, we'd get the same answer as if we did the whole vector and only got the y value from the entire vector, so there's no difference. The conclusion. Using drag increases the accuracy of our model, and taking into account of different factors can help us. This shows the complexity of the universe and inspires us to be more precise. Thank you.